Welcome everyone to the Fireside Chat and AMA with computer scientist Dr. Viral Shah, who is the co-creator and CEO of Julia Computing. Julia is an open source language for high performance technical computing and data science created by some of the best minds in mathematical and statistical computing. Its users and partners include, but are not limited to, IBM, Intel, DARPA, Lawrence Berkeley National Laboratory, and the National Energy Research Scientific Computing Center. The Julia programming language can be used for specialized domains such as machine learning, visualization, and data science. Now enough for me. Let's give it up for the person you're all here for, Dr. Valshaw. Please take it away.
Hello?
Yeah, no, we can hear you. I'm just gonna go off the live stream, but you can feel free to talk. The hackers can hear you.
Oh, okay. All right. So, what would it be possible for me to share my screen?
Yep. Here you go. And you can just click the share, and you can share anything that you would like to.
Yeah, I have a short presentation that I sort of put together just to sort of get people a flavor for what Julia is all about. But I'm wondering if like are people out here in the chat? Like, can I communicate with them in the chat as well?
Yeah, you can. So when any hacker has any questions or anything like that, they will you can see it on the side.
Okay, and so let's get started. What I would really like to do is maybe start out by asking people, like, what programming languages does everyone use, and how many Julia users do we have? I mean, uh, so I am in something called private chat, I suppose, or comments in the StreamYard. So if people can type out in the chat what they're using or what languages they use, that would be fantastic. While I set up my screen. Do we have no takers for the chat? Is it right? Or maybe people are typing stuff out and I'm not seeing it. Oh, I see it in comments here. Okay, thank you. All right, so Python, JavaScript, Go, more Python. All right, let's get a few more of those kind of coming through. In the meanwhile, can you guys see my screen? All right, can someone give me a thumbs up if they can see my screen? Okay, perfect. All right, so what I wanted to talk about is a system called uh, is about the Julia programming language. And I like to talk about Julia Hub, which is which is the platform for running Julia, but that's not going to be my topic for the day. I want to start out by motivating certain kinds of use cases. So I love the comments that are coming in. Let's have a few more comments. So I understand what programming languages you guys are using. Let's have a little bit more about what's the right word for it, what applications. So, right, like, I'm assuming if someone's using JavaScript, they're probably building UIs. But for the people using Python or Go, what kind of applications are you guys building? Are these numerical applications, machine learning applications, like networking software, crypto mining, right? So I would love to hear what people are doing in all these languages and what kinds of applications you guys are all building. But let me tell you about why Julia, right? And why I'm one of the why me and my co-founder started the Julia project. And if you look at it, there's a million x performance available today than was possible just a few years ago, right? And I've deliberately picked this number so that it's intriguing. And everyone sort of heard about the Julia design and about its influence on other languages, that we started Julia to solve the two language problem, right? Something that is as easy as Python and as fast as C. And Julia's multiple dispatch. If you're an object-oriented programmer, which is single dispatch, Julia's multiple dispatch. It's more functional. You can find all these things on the internet, right? Even while you're hearing me speak, you can go and Google Julia, go to julialang.org and see what Julia is all about. And all of you, would be able to, are programmers yourself, so you should be able to figure out all the things about Julia in all these buckets, right? But what I want to talk about is, what's our place in the world, right? What is it that we do that is significantly better than everyone else, right? And if you think about it, science and technical computing and engineering and all these technical domains have not been well served by the world of software and programming tools and developer tools. And today, everything around us, it's every data science is everywhere, machine learning is everywhere. But that's, as soon as you go beyond that into the real world, you're building new products. You have, we're building new rockets and sending them out at rates like never before. Electric cars are being built, new batteries. I mean, the world around us is changing at a pace like never before. And all the people, some of the smartest people in the room who design these things, right? The scientists and the engineers and the quants and the AI people or whatever it is, right? Whoever it is that's doing any form of applied mathematics has been underserved, has had very poor tools. I mean, let's think about it, right? Like if I was an engineer today, I could either use MATLAB or I could use Python, which would be a bit slow. I could use R if I was a statistician. And all these languages, which are the right ways for me to do my work, are incredibly slow. However, the world has moved forward, right? So if you look at my slide here, right, the world of programming languages and tools is fragmented. But something like Julia can give you 100x faster, can be 100x faster. It's not going to be 100x faster for every program that you write. But, for certain kinds of programs where you're not calling into C libraries under the hood, you're going to see that Julia is often about 100 times faster. The second thing is that, in the last few years, machine learning has reshaped computing, right? And if you can train, the whole software 2.0, manifesto and all that stuff, right? So if you can train a machine learning model on something, chances are the inference is going to be about 100 times faster. I mean, sometimes it might be 1,000 times faster or 10x faster, but if something is trainable, machine learning can really give you, inference on those models that can be 100x faster. And being able to apply machine learning to a variety of different problems is difficult, right? Especially because a lot of the machine learning that we know as of today has been driven by what I call sort of, driven by Silicon Valley, right? In some sense, right? Where you have data-driven machine learning, you have tons and tons of images and videos and text data, all of that stuff that was created on the internet, and then amazing machine learning models and computers have been put together. Computers have been designed, right, like Google's TPUs, to apply these large-scale models to these data sets. But if you're an airline manufacturer, right, if you build rockets, if you're a drug designer, right, like if you're your data is not that large. Your data tends to be small, right? Like if a drug company wants data, they have to go out and do a clinical trial and spend hundreds of millions of dollars. Or if you're an aircraft manufacturer, you want data, you have to send a plane in the air to collect the data. So traditional industries outside of internet businesses tend to have sparse data, and they tend to be model driven, right? We understand the laws of thermodynamics, we understand the Newton's laws and all of this good stuff. We understand science in the world around us, and that world does not have as much data as the internet world, but you can still benefit a lot from machine learning in that world. And the question is how, right? And I'll speak a little bit about that, but the quick one-line answer is that it is differentiable programming, right? That if I can write a program and I can take derivatives of my program, then I can optimize, and I can do all sorts of fun things, and I can do all kinds of machine learning algorithms. The key is to be able to differentiate any program, not just a particular small class of problems. And then, of course, when I say the cloud is the way forward, that's another factor of 100 available to you, whether you go distributed computing or you go with a single GPU or multiple GPUs, or access to the kinds of machines that you may not otherwise have, unless your employer provides them to you, or unless you're just very rich and have your own data center. right? So there are these three factors of 100 which can in theory be compounded, and you get, there's a million x performance available for a large class of problems that we've not even imagined. What would you do if you had a million x performance, right? I'd love to see some comments in the chat there. If you were able to do things a million times faster than today, or even just a few years ago, what would you do? And Bitcoin mining is not an acceptable answer. So please have those answers coming through the comments. And in the meanwhile, I will talk about what we are doing with Julia Computing and with Julia, right? So we're doing, we're building this open source Julia ecosystem with a million users out there, right? Like the Julia ecosystem is about 1 million users, 5,000 packages. It's got, all this amazing stuff. And as the community grows, we are working on building Julia Hub, which is a SaaS platform for data science. We want a supercomputer at your fingertips for every single user. And we're building it such that a number of different domains like pharma simulation, physical simulation, circuit simulation are built on top of Julia. So that million X, we think that there is no better way for us as computer scientists to spend our time than in the service of real science, right? What can we do to make drug discovery faster and cheaper? What can we do to simulate the world around us? What can we do to design new kinds of semiconductor chips or whatever it is? And what can we do to make it possible for everyone around in the world, take these ideas and put them in a marketplace, make it available to everyone. So that's sort of the platform that we are building out here at Julia Computing, and it's all powered by Julia. And it's bringing on board some amazing new applications. All right, so I have, that's the wrong button on my mouse. So I have a question here. Can I tell you guys a little bit about multiple dispatch and how Julia uses it to its advantage? That's a great question. So let me talk a little bit about multiple dispatch, right? And I would encourage you to go and talk about. I would encourage you to bring this question up in a few minutes when we switch to the question and answer. So let me set the stage. But in the meanwhile, you might want to bookmark the unreasonable effectiveness of multiple dispatch, which is a talk by my co-founder Stefan Krapinski that I think he gave at one of the Julia cons a while ago, and I think that's the one that will give you all the meat on it, and I'll give you the short version of it shortly. But what's the Julia community like, right? So it's large, it's growing rapidly, millions of downloads, tons of YouTube views. Come hang out on the Discourse forum and our Slack channel and our Zulip channels, right? Like the community is really, really active and encouraging and inviting. And so this is our Discourse forum views. Julia's in the press all the time. Number of packages is fantastic. Growing on all the programming language rankings, interoperable with all the languages, increasingly covered in all the press, 1,500 universities, 10,000 companies, right? Why do I share all this with you? Because, sometimes people are like, oh, Python's everywhere. Why should I learn Julia? Well, this is the reason why you should. And again, the reason I'm sharing all this with you guys is so that you have, you all are technically very adept at figuring out what the programming language is all about. What I want to share with you is the evidence that Julia is here and it's huge and it's right now. So these are some of the universities teaching Julia. One of the amazing things about the Julia community is that, it started out on GitHub, and all of our packages, well, not all of our packages, but many of our packages are actually organized on GitHub as open source organizations. So there's over 100 open source GitHub organizations, and that naturally creates sub communities. So someone who, people who want to work on energy or data science or collections or data structures or economics or climate science, machine learning, deep learning, whatever it is, right? Like there's an org for it, right? Like whatever that you want to do in Julia, there's usually an org for it. And if there isn't, you can start one and collect people from a variety of different disciplines and bring them together. I believe personally that the Julia community has a quality to it that I haven't seen in other communities, that it has brought together incredible practitioners, professors from some of the top universities, a lot of bored grad students who would rather write some amazing code rather than do whatever it is that they're procrastinating from, and so on and so forth, right? But it's a community of eclectic people, but that has just grown by leaps and bounds, and you'd find yourself very welcome there. Is Julia kind of like DN? I sorry, I don't know what DN is. All right, I'm gonna pause on some of these questions, and I'm gonna just share a few more slides so that we can then come to the Q&A section a little bit later. Give me 5 more minutes here. So why Julia, right? The ease of Python with the speed of C. If you look at some of these charts out there, right? So you've got this is a computer language benchmark scheme, the very first thing that I have out here. And Julia is the only dynamic language on this list, I believe. Almost everything else is statically typed, and Julia pretty much is holding its own against like C and Rust and Fortran out here, and way faster than everything else. And languages like Python and R don't make it to this first chart on the computer language benchmark scheme. It goes to the second one. But there's this amazing set of benchmarks for graph processing that someone put up where Julia does extremely well with Julia's light graphs library. There's k-means. There was an amazing k-means package that someone wrote in Julia. It's not the full scikit-learn, but they were able to get 100x faster performance than scikit-learn there. A common data set, a common benchmark that I like is the data frames benchmark, and the guys over at h2o.ai had put together this amazing benchmark. And it, we in the Julia world, we love nothing much. Like when we see a performance challenge, we have to get out there and get to number one, right? And dataframes.jl out here started out much lower, and we've steadily been climbing up, and we won't rest until we usually sort of get to the to the topmost position here. But dataframes.jl is Julia's data analysis package. It's kind of like pandas in Python, but it's multi-threaded. So because of Julia's built-in multi-threading, you as a user can leverage multiple cores, but then Julia's libraries can also use multiple cores, and that always gives you some amazing performance. One of the cool things about Julia's multi-threading is that it's composable, so that if you as a user write something that was multi-threaded, and then you call a package that was written by someone else that is also multi-threaded, you get Julia will sort of coordinate across all of these things and not oversubscribe your system, which is sometimes what happens in systems like pthreads. So composable multi-threading is a huge big deal. And then CSV loading, a lot has been said about this thing on the internet, but the quick takeaway is that Julia's multi-threading makes it very easy to work with large data sets that often happen to be in CSV files and across lots and lots of directories. Julia also includes support for GPUs. So native GPU programming is part of Julia in the Julia GPU organization and ecosystem. And we have very good support for NVIDIA GPUs at the moment, but folks are working on AMD and Intel GPU support as we speak. The benchmarks speak for themselves. We match CUDA-C in performance with a native Julia compiler. So it's the only other language that I'm aware of that's as good as or probably better than CUDA C++ in terms of ease of use, but is practically on par with a lot of the key features. And there's tons and tons of noteworthy applications, people using it for pharmaceutical workloads, which is all the drug discovery companies are doing that. And the supercomputing folks in Switzerland used it for a climate project, tons of multi-physics simulations, and Jonathan Laurent from Carnegie Mellon has AlphaZero.jl, which is a Julia-based implementation of AlphaZero, which is really fun to work with. Really small amount of code and can do a lot. This is the last thing I want to talk about in this part, and then I think we can switch to the question answer session. But what really makes Julia stand out is its ability to do differentiable programming, right? And if you're sort of plugged into the world of data science and machine learning, you know that software, you know about the Software 2.0 manifesto. Differentiable programming is the way of the future, right? Where not only do you apply automatic differentiation to neural networks, but you want to be able to apply those ideas to any program, not just constrained set of programs that are called neural networks, right? So if I can apply differentiability, if I can differentiate any program, then I can optimize it. I can put it into a deep learning loop, and I can combine it with data. I can do all sorts of interesting things. If I'm an engineer, I can build a digital twin. If I'm an economist, I can optimize prices. If I'm a control engineer, I can go and design optimal control, right? So differentiability gives you so much, and it gives you an automated way to work with very large data sets and perform the optimization process. And Julia makes this possible across, because differentiability in Julia is built in at the compiler level. You can actually go about taking derivatives of many different kinds of Julia programs. I mean, it's not as easy as I make it sound like, but it is way easier than in most other languages. And you want to pair all of this up with working on large data sets, working on distributed computing, working on GPUs, working on TPUs, or deploying it to a Raspberry Pi or an ARM system. So this is the kind of stuff that the Julia the Julia community and Julia computing both care about very deeply, and that's what I spend a lot of my time on these days. So here's an example of bringing all of this together. It's a little bit of an older example, but this is Julia running on the world's fifth largest supercomputer at Lawrence Berkeley National Laboratory, processed 178 terabytes of Sloan digital sky survey images. And this was actually applying a very custom machine learning algorithm. The challenge was, how do you figure out what's the right, in the Sloan digital sky survey, right? The purpose of it is to catalog every light source in the universe. But the problem that you face is that you're operating at the limit of the instrument. And so when you see a pixel, is it because of noise in the instrument that's measuring it, or is it because it's an actual light source somewhere out there in the universe? And there is a fairly sophisticated machine learning algorithm that was designed by Jeff Ragier at Berkeley that figures this out. And we applied this to the entire data set and counted 188 million light sources. And that was just this pretty phenomenal science that came out of that work. I have a lot of other stuff around, differentiable programming, about how we at Julia Computing are applying it to packages and programs like Julia Sim, where you can go out and simulate the world around you. But I think this would be a little bit too involved for our conversation at the moment. I'm happy to dive into it. But Julia is entering all sorts of interesting domain-specific areas, like I talked about, whether it's pharma simulation or industrial modeling and simulation or semiconductor simulation. And we have a lot of new stuff coming out. It's all going to be talked about at great depth in JuliaCon, which is our annual conference. If you go to juliacon.org, you'll be able to find out all about it. It's a free registration for this year, and it's completely online. So please go and sign up at JuliaCon so that you can learn a lot more about Julia. In the meanwhile, I will pause my presentation and stop sharing my screen so that we can come back to the AMA. All right. Is one of the moderators probably going to join us for the AMA part, or how are we going to do this? Or do I expect sort of questions to come in over the chat? Or
yeah. So 1 second. Thank you so much for the talk. It was really innovative, and I learned a lot of new things myself. Let's segue into our AMA portion of the session. To ask a question, just drop it in the chat, and we will try and get to it. Or also try to put it in the Discord server as well, in the general channel. If the YouTube chat does not work, I'll start off with some pre-submitted questions, and then we'll get into some questions from the audience. So let's get into it. So the first question that was pre-submitted to us was, so Dr. Viral Shah, many attendees in our hackathon are beginners who are looking for something to spark their interest into the programming world. What started your interest in programming and coding?
Yeah, I was, I went to school in India, in Mumbai, and my school actually in 8th grade had had a computer lab back in that day. I mean, it was different. You had to actually go to a separate room and there were these computers with these floppy disks and stuff like that. And basic GW basic was the first thing that I learned. It was part of the syllabus. I don't think most of my classmates enjoyed it, but I was just completely taken in by it. And that's how I got started. My interest grew largely from a very young age with scientific computing. I actually taught myself, all my physics and chemistry by actually writing out programs for every little thing that I learned, and that was incredibly fun for me. Maybe not fun for everyone else, but that's kind of as I think back about it, I got started with scientific computing by just trying to teach myself programming and science at the same time. So that's my story.
Yeah, no, I completely agree with you. So going off of that, when how you first got started off, once you got to college, what is something that you learned in college that has stuck with you even till now? And it can be anything.
Oh, that's a tough one. What did I learn in college that stuck with me? Yeah, so I went I pursued my undergraduate studies in India. I got a Bachelor of Engineering from PPP College of Engineering there, and then went to UC Santa Barbara for my PhD, which was quite a learning experience, and one of the most enjoyable parts of my life. Um, but I'm sorry, I can't think of something that has stuck with me since then. I mean, I could sort of give you the standard answers of, follow your passion and all that kind of stuff. In my case, I will share with you that I did not know how much I enjoyed scientific computing until I stopped trying to do it and tried to do something else. Um, like many computer scientists, I always used to wrongly believe that nothing could be better than doing theoretical computer science and doing theory. And I just spent a couple of years trying to do that very badly, and later on realized that I missed programming and I loved science. And coming back to my roots of what got me excited was essential in actually getting my PhD done. And I applied that broad principle to the rest of everything I do, that time is, life is short, you don't have enough time. Stop doing things that are sort of, that you're not good at, that you might not enjoy, and just do the things that find your purpose in the world, right? And that's the question that I ask every day.
Yeah, no, that is a very good answer. And one more question is, who is your tech role model throughout the years?
um I've had, I've had many mentors over the years. I think more than role model, it's mentors that matter a lot. Role model is someone who might be distant that you might want to emulate, like, someone might, you know have Steve Jobs as their role model, or Mahatma Gandhi as a role model of someone who I personally think of as someone, that growing up in India, you learn so much about Gandhi that you might wonder, what's the big deal about him. But then, I personally went back to India after my PhD to work on a project called Aadhaar, which was the government of India's identity project. And it was an eye-opening thing to see what India is about, and the diversity, and so on and so forth. And that's when I sort of look back through my history books and realized what an accomplishment the Indian freedom movement was, and what Gandhiji achieved. So that would be a role model of someone, which I can see all the current role models that people would have, right? In the tech industry, for example. But when I step back and look at like things that people achieved, like I just cannot fathom what got him to do what he did. And I continue to try to find that answer. But I think what's important for all of us at earlier stages in our careers is mentors, right? Who is that person who can help you, who can lead you by the finger, and take you to the next level? And I've been fortunate enough to have many different mentors at many different stages. In my through my undergraduate days, through my grad school, my PhD mentor, and even as I run my company, I've had several people who've mentored me as I run Julia Computing. And so I would say surround yourself, identify those mentors, ask yourself how you can be of value to them so that they can invest the time in you.
Yeah, no, that is a very good answer. So, switching to Julia computing, what is your vision for the future of Julia programming language? What are your future plans with it, or any ideas that you may be expanding on?
Sorry, you broke out there for you broke down for a second.
Oh,
Is
I'm
the
sorry.
question that
I'll
what are the
repeat.
plans
Yeah, I'll
for?
repeat the question. Someone asked, "What is your vision for the future of Julia programming language?"
Okay, yeah. I mean, we set out to build the best programming language for technical computing being a very specific focus, but we did not build a language that was only for technical computing, right? What we set out to do was build a general purpose language which was going to be a dynamic programming language, very easy to work with, very easy to learn. And we specialized it for technical computing in the early days because of the kinds of libraries we built and the kinds of applications we sought out and the kind of community that found us. But Julia, by no stretch of imagination, is restricted to technical or mathematical programming. It's actually a fully general purpose language, and probably one of the few dynamic languages that is incredibly high performance. And I think that combination is so powerful that it should, I mean, right, if you play out, like, once you have an advantage over something, right, that advantage tends to compound over time. And so over the last 10 years, Julia has been doubling, at least since it went public, since it was known publicly, it has been doubling in adoption every year, year after year, no stopping. And I see no reason for that to stop. And I see that it will expand from its numerical computing and technical computing and machine learning niche into doing all kinds of things, and becoming a programming language that people use for just about anything that they can imagine. So I feel like if you believe the software 2.0 kind of story that programming is going to change everything, and within programming, machine learning is gonna and models are going to change everything, I think Julia has a huge role in that future. It's unclear what that future looks like, but it's clear that Julia is part of it. And I mean, we have a lot of things that are planned for the immediate next few years in terms of what we want to do with the language, but eventually it's a community driven process. So it doesn't matter what I want or what you want or what my colleagues Jeff or Stefan or Keno want. It's about who is contributing code and who's bringing new ideas to the table, and that is how the language evolves. But I'll give you some examples from the past, right? So multi-threading was a major new feature that we added, and we started work on that about 6 years ago. And I think it made its way into the language about a couple of years ago. And that was huge, right? Similar new feature, a major new feature that was added was GPU computing, which was done by Tim Bassard. And he created, the Julia GPU compiler stack. And that is a phenomenal project continuing to, still grow forward. The most recent one is adding differentiable programming capabilities to the Julia language, originally started by Mike Innes as part of the Flux project, and then subsequently Keno Fisher, who's one of my co-founders at Julia Computing, took over those ideas and bolted them into the Julia compiler so that it would be really fast and high performance. So these are significant major language level things that we have done. And I mean, these are just the big features, but if you look at our release notes, you'll see lots and lots of new things that have been done over the years. And going forward, I think there's another year of just a focus on differentiable programming that we need to do. But beyond that, I mean, we don't have a plan, right? We don't have a roadmap of year 2. This is what we're going to do. Year 3, this is what we're going to do. It's what the community decides needs to get done.
Yeah, no, I completely agree with you. Earlier you said that Julia programming is going to be a very powerful thing, and so you give me the sense that many new self-taught programmers are going to start to utilize Julia programming. And so, a question that one of our hackers have is, how easy would it be for a self-taught programmer who develops apps and whose background is primarily in Java to transition to Julia?
It's not very hard at all, right? In fact, Java is a lot more Java is a statically typed language, right? So you have to write a lot of code in Java to get a few things done. you'll find Julia to be a lot more compact. And as a language, you'll find it to be sort of designed with a different set of principles. And so don't try to map the Java, your Java mindset onto the Julia mindset, but approach it with an open mind. And you're going to find a couple of things. You're going to find that it's easy to learn. It's very friendly because it's interactive. And you're also going to find a few things that you don't like you might find that there isn't enough documentation available on the internet because Julia is a younger language than Java. And I would suggest just kind of join the communities, join the forums, incredibly friendly, and get yourself a good Julia book. That will be greatly useful in your journey. The Julia manual is also very high quality and a good place for you to learn, as is juliaacademy.com, which has videos. So if you like to read from the manual, we've got that. We've got video tutorials on Julia Academy, and we've got lots and lots of other learning materials that are all linked on the website. But I would say that if you know how to program in one language, you should be able to pick up Julia in less than a week. But just like everything else in the world, it's easy to get started, but mastering something just takes a very long time. And I like to tell everyone that even I'm still mastering Julia because I still don't know what's the maximum possible thing that can be achieved. We're always building new abstractions and figuring out how to incorporate them into a new programming style, into doing things better, into doing things faster, and building more and more sophisticated applications with less and less effort.
Yes, I completely agree with you on that. Julia would be an easier transition, and it's not a hard language to pick up. So you did, say to read some good books about it. So a question that we have is there any good books for Julia programming languages? If not, would you plan in writing and publishing a book about Julia computing, if you haven't already?
We haven't written a book ourselves, but there are, and that is because there are just lots of fantastic books out there. There is possibly a world in which we do decide to write a book, but if you go to julialang.org/learning, there is a books section where we maintain a list of all the books. And I believe that, sorry, this is, let me just, I'm just looking at the list right now. There's a particular book that I wanted to suggest. So Hands-on Design Patterns and Best Practices with Julia by Tom Kwong is a pretty good book for if you just want to learn the language. There is there's a recent book called Julia for Beginners from Eric Engheim that came out. That was pretty nice. But then there are specific books, like if you're learning linear algebra, then how do you learn linear algebra with Julia, or image processing with Julia, or machine learning with Julia, or so on and so forth, right? Or optimization with Julia. And those are all books written by professors at some of the best universities. So all of them are listed on the Julia website, and they're all pretty fantastic. But there's quite a few different kinds of books, especially for younger programmers. There's a book that Tanmay Bakshi has written. Tanmay teaches Julia for Beginners, a springboard to machine learning for all ages. And I would recommend that book, especially for people, for kids, and stuff like that. So there's just a lot of different books out there, and which is why we haven't written a book ourselves.
So we have a question in the chat. How does Julia deal with GC pauses?
Oh, okay, that's a good one. So Julia is a garbage collected language, and how do we deal with GC pauses? So, well, we pause for GC, and we try our hardest to make our GC as effective as it can be. There's definitely a lot of work that can be done there to improve it. What we usually do is we provide lots of good tools to programmers to measure memory allocations and to reduce them altogether, because the best way to avoid garbage collection is to not create garbage in the first place. And that's sort of one of the things we like people to do when they're writing programs where they can't deal with GC pauses. But GC pauses are just a fact of life, and we just keep trying to do better and better at them. We have sort of introduced some capabilities for doing bounded time garbage collection, and features like that. We have some knobs that you can tune for applications that care about those sorts of things. But by and large, people who care about those sorts of things have been able to write their Julia programs with minimal memory allocation.
Yeah, so that is a great answer to the question. Um, another question one of our hackers have is, if you were to restart the Julia project from scratch, what or how would you change it? Or what aspect would you modify?
Of Julia, if I started from scratch again?
Yeah, coming from the experiences that you have already gained.
Oh, that's a tough one. I mean, it's not the kind of thing you think about, right? But there are. So I have personally always focused more on the mathematical libraries in Julia as compared to sort of more aspects of the language design itself, which my colleagues Jeff and Stefan have driven. I'm sure if you ask them, they might have a few things on their minds that they would have done differently. Um, but and one of the challenges that we run into on a regular basis. So I could tell you about all the things in math libraries that I would like to do different if I started again, but I also know that they're not practical or meaningful. For example, our dependencies on things like the BLAS libraries, which we thought was a great idea, turns out has kept us bogged down with all sorts of performance challenges. But you know Julia was not ready to write its own native BLAS until today. So what would you do, right? You had to. It's never a straight path, right? That's my point. That it's we knew what the ideal solution to getting many things done in Julia was, but in order to sort of get to today, over the last 10 years we made lots and lots of incremental and small decisions on a day-to-day basis. And so the path is always meandering, right? It's never a straight line path. It's never the shortest path, but it's the path that makes sense and that allows you to build on top of what you've built, and so on and so forth. So and this has always been one of our driving principles in Julia development. Like, even if you go back all the way into Julia history, you'll see that within the first few weeks of the Julia project being started, before it was known publicly, this was in 2009, you could already do useful things with Julia. You could generate random numbers, you could create arrays, you could do some matrix arithmetic. And so we've always been driven by, let's do the reasonably expedient thing at the moment to satisfy what our users need to do and what they need to build, while then seeing what sticks in the longer run and then doing it better and throwing away the old stuff, throwing away the technical debt. One of the things that that has been a challenge for us is LLVM, which just takes up a lot of our compile time today. And could we have done something differently there? It's unclear, but it's something that we like to think about, that maybe there was some magical other framework that we could have used instead of LLVM.
And so, speaking on building, what was the most challenging part, at least for you, in making Julia?
I would say that the technical challenges were always, like when you start to set out to build something where you sort of solve the two language problem, right? Like the speed of Python, the speed of C and the ease of Python. That's a pretty tough problem that you've already set out to solve. Intuitively, we knew that it is solvable even before we started, but it was not obvious until we actually got a couple of years into the project that we could achieve that. But those are technical problems. I would say that as the project grows, it's always the people problems that are more difficult to work with, just like everything else in life. That the technical problems are hard, but you can sort of you can push through them. But the people problems, around growing a large community and having all the different kinds of voices and the pushes and pulls, and everyone wanting different things, even though all the things that everyone wants are in their totality amazing for the project. But there are always there are always things that you have to do, and difficult decisions you have to make. And sort of all of us being the founders of Julia, sort of being at the center of this community, are often sort of put into positions where we have to make some hard decisions around many of these things. I think we've been incredibly lucky that we've had such a great community, because these kinds of challenges have been largely at a minimum, and even in cases where we had some problems, we've been able to persuade those people to see to sort of come around. But it's you just can't please everyone all the time.
Yeah, no, like it completely makes sense. And so Jack here has questions. Are all functions in Julia virtual? If so, how do you optimize the lookup?
So a lot of Julia is actually not, Julia can be fully dynamic. It is a dynamic language, and you can write very dynamic code where you might worry about the cost of these things. But almost a lot of the way the Julia compiler works is that it does ahead of time. It runs a type inference pass. It figures out the types of all the variables in your program, and it lowers the code, and then at that point it ahead of time generates native code and then runs it, right? So a lot of, from the point that Julia's done its type inference, it's a pretty straightforward path from there to, compiling it down through LLVM into native code and running it. And it does not look, it's not like everything's virtual. If in it's actually quite the opposite. So we don't worry too much about the costs of these kinds of lookups. But there, in situations where the Julia compiler can't figure these kinds of things out, it does have to then go about and worry about these things and the costs of searching through the multiple different options that are available. And that's just expensive, and it's slow. We I would not be the right person to talk about how we optimize these things, but maybe on a future version of this, you can ask the question to my colleague Jeff Bezanson.
Hmm. And so one of our hackers have asked us, tell us a bit about multiple dispatch and how Julia uses it to its advantage.
Yeah, so like I said, there's a fantastic talk by another of my co-founders, Stefan Karpinski. So definitely find that and watch it. It's called The Unreasonable Effectiveness of Multiple Dispatch. But the key thing, if you sort of feel, everyone knows probably what the definition of multiple dispatch is and how it, is different. And just like I explained right now, right, how you can go through all of your how Julia sort of, how the Julia compilation process works, right, with the type inference and everything. And that's very deeply tied with multiple dispatch. But if you step back from all of those technical details, what multiple dispatch does is it has an amazing social contract, right? Because what's a good language feature? Good language feature is one where the language designer provides it to the user in order to get some information, and the user is happy to provide that information in order to get some value out of it, like performance or ease of use or whatever it is. And these things can sometimes be trade-offs, right? That you as the language designer, you require the like statically typed languages, right? You as the programming language designer ask the user to write the type declaration for every single thing that they use in their program, so that the compiler can then go ahead and generate fast code. Well, I mean, what if you didn't have to do that? What if you provided an interface to a user where there was a different kind of user interface where they didn't have to provide that information? The compiler could still figure it out. And that's a great feature, right? And so multiple dispatch is one of those things that allows you to do, especially in Julia. It's this language, it's this social contract, which is amazing, because as a user, you are writing your code in a way that is useful to the compiler, but is also useful for yourself, right? So think of the plus function in Julia, right? That when you do multiple dispatch on plus, you have a separate function for integer plus integer, and a separate multiple dispatch for integer plus float, and the third one for integer plus some other data type, right? In fact, if you start Julia and type methods, and in parentheses plus, it'll show some 300 odd methods that Julia can pick from. So now these 300 methods have been all written at different parts in the Julia code base, and they're all separate functions. And as a user, you get readability, right? Because now when you write a new package, you can add a new plus method that works on your data type. So it gives you a separation of concerns. You don't have to go into Julia and dig into Julia's implementation of plus and then add your little addition out into that mix there, right? You can do it separately in your own code. And the compiler, the language designer, benefits greatly from that, because now as a user, because of multiple dispatch, they have written a new definition of plus that operates on new data types. And when the compiler sees a call to plus which is using those new data types, it can compile the code for that particular, exactly for that particular set of inputs. And so multiple dispatch is this amazing feature in the language that allows the user to separate out and write their code in a very nice way. And at the same time, the designer is able to leverage that information and generate very high performance code. So very few language features often have this kind of win-win because it's always a give and take. But I feel like multiple dispatch has been something that has been, pretty fantastic on that in that regard for us. And is one of the reasons why people like to come to Julia.
Mhm. So we're gonna do a few more questions before this workshop has ended. So a question that one of our hackers has is, how does Julia offer an advantage in comparison other memory-safe languages such as Rust, and why do you think it's a better choice for machine learning-based pipelines in the longer run?
Machine learning based sorry, what was the first part of the question around Rust?
Yeah. How does Julia offer an advantage in comparison other memory-safe languages such as Rust, and why do you think it's a better choice for machine learning? Yeah.
Yeah, so Rust is in a very different design space, right? Rust is optimizing a very different part of the language design space than Julia is. So I would say that Julia is not actually competing with Rust in mindshare there, and in fact, many people like to use Rust for their low level stuff and Julia for their their high level machine learning, technical programming sorts of things. For anything in machine learning, I mean, I already sort of spoke at length about how Julia is going all in with differentiable programming, because what's machine learning at the end of the day, right? You're optimizing something, and you have data, you're fitting a model to that data, and off the most some of the most successful methods in fitting that fit models to data are gradient based, right? You're doing gradient descent, and how do you do gradient descent? Well, you compute the derivative, and then you sort of go in the go and take a step that will minimize your loss function. And the question then becomes, why should only neural networks be optimized? Why can't you optimize other kinds of programs? And that's really why Julia is so essential. It is so much better for machine learning than anything else, because many of the things that make machine learning interesting and useful can be broadly generalized in the Julia language to do many other kinds of things and support many other kinds of problems. So you can bring machine learning into scientific problems where which has traditionally been hard for people to do. If you look at the sciml.ai website, which is Julia scientific machine learning project run by Chris Rackauckas, you'll see the kinds of innovations that have been possible because of all these possibilities in the language. So this is really why. And then I would suggest even going back and if you Google for on ML and PL, there is a blog post on Julia and machine learning, where we sort of set out a manifesto for why Julia is the right language for machine learning. And even though it's a bit dated now, it talks about many of many of these ideas in a nice way.
Yeah. So we have one more question before we wrap it up. If you were to invite someone to develop Julia with you and your team, who would you pick? And it can be anyone in the world.
Anyone in the world to develop Julia with us?
Yeah, it can be like anybody, any
Yeah,
programmer,
yeah.
anyone.
I mean, you guys really asked some hard questions that I've never thought about. I'm sure my co-founders have different people on their minds, but one of the ones that always used to come up was someone like Chris Latner, who's the creator of the LLVM project and Swift, right? Would be a pretty phenomenal kind of person to have, come in and mess around with Julia and do interesting things. I would have to. I mean, these are hard questions. I would have to think at length about, like, if I had to pick someone. And then the question is, do you get to pick someone today, or do you get to pick someone from from the past as well?
Oh, you can pick anybody.
I know. I would. I'm probably just gonna leave that at this point.
Okay. So we have one. Well, we have time for one more question. Um, and the question is, what is the difference between a machine learning / data science specific language versus a machine learning library or framework? and frameworks such as TensorFlow and PyTorch?
Yeah, that's actually a very good question. It's actually a pretty deep question as well, right? What's the difference between a machine learning language and a machine learning library? And so libraries are usually less general, right? So your first, when you're trying to do something new, when you're writing, when you're sort of when a new domain comes up, the question is, should it be tackled as a library or is it a language level feature, right? And the answer usually almost always is that it's a library, right? That if you have a new algorithm, if you have a new kind of scientific method, if you have anything, you start out by writing it as a library. And then there is a subset of the broader set of programmers, a very small subset that would usually be interested, right? A small subset can be tens or hundreds of thousands of people, right? Because there's like tens of millions of programmers out there in the real world. So when you come up with something new, you usually start out by writing it as a library, and then you have the benefits of the programming language and all the programming language tooling and profilers and debuggers and other libraries that you can build on, and so that's usually sort of how you get started. But then there are things at certain points where you look at a large class of emerging applications and algorithms, and you ask the question, wait, I'm seeing something that is common across all of these different use cases, and this is something that might benefit from being present at the language level. And that's how you sort of start asking if something should be a language level feature. So a good example would be like there used to be sort of this time when threading used to be a library feature, right? That you could you had threading libraries, or more than threading, right? Like parallelism stuff, that they often tended to be libraries, right? And you could use Spark to distribute your to run large scale computing jobs, right, for example. Or you had user space threading libraries, and eventually language designers decided that, hey, these things are so common that they need to become language features. And you don't want a threading library that's common across every language, but the language should have its own view on what multi-threading looks like, and that's what led to Julia's multi-threading. And similarly, Julia has views on how distributed computing happens. And similarly, Julia has views on how machine learning happens, because machine learning is not a language feature in Julia at all, right? Machine learning is actually a library. So usually you would use the flux.jl or many of the other machine libraries out there. But then we look at some of the underlying things inside those libraries, that when we look at Flux and when we look at Jump, which is our operations research, or logistics, libraries, or when we look at something like Turing, which is probabilistic programming in Julia, we see that derivatives are being computed everywhere, and doing them just in a library like the way PyTorch does it would not be sufficient. TensorFlow is a little bit of a weird situation, right? Because in TensorFlow, you're actually creating this graph, this compute graph, where you're sort of creating a compute graph that's almost like an abstract syntax tree. And then TensorFlow has a compiler that's actually compiling it and running it. And this is why TensorFlow is uncomposable with anything else in the Python ecosystem, right? That TensorFlow usually has its own images library, and it has its own IO, and it has its own data frames and its own everything, right? Because TensorFlow is actually a language that happens to have sort of surface syntax in Python to construct that language, the AST representation. But PyTorch is a little bit closer to a library. I know the lines are getting blurred nowadays in what PyTorch can do. I mean, PyTorch has more compilation. TensorFlow has, JAX, which is kind of more Pythonic. And then Julia's kind of got, its own differentiation tools and its own machine learning libraries, which are completely designed and stacked up in a different way, because it's being done by language designers working very closely with the end users, which is, I think, different from what TensorFlow's goals were, which were to sort of run on very large scale things like TPUs, or PyTorch goals were, which was more focused around ease of use. And then from there, it sort of has grown into, the amazing set of capabilities that it has today. So it's just all exploring different kinds of things.
So unfortunately, we are at the time to end this AMA. I hope everyone enjoyed asking and learning more about Dr. Raul Shah and his work at Julia Computing Language. Thank you once again, Dr. Raul Shah, for coming to the event and informing/inspiring everyone through your engaging keynote and exciting AMA. We've had a very great time with you over here. Thanks everyone. Thank you. Well, thanks everyone who tuned in. If you guys missed a past AMA or a past workshop, Feel free to check out our YouTube as we upload them to the channel afterwards. There's also another event that is happening right now, which is Toyo Quest's workshop. If you guys are competing for that for their prize track, I would highly recommend you guys head over there and see you guys later.